Hello, and welcome to the third recording session associated with probability. This is Dr. Leslie Ann Asmus. In this recording session, we're going to focus on two additional concepts, one being independence and the other being we're going to look at a variety of fundamental rules. And back to the original question of, well, how do we assign probabilities to different points of interest? And so we're going to look at these different concepts that impact that assignment. Okay, so the first is independence. Two events, A and B in S, are independent if and only if the probability of the intersection, probability of A and B, so remember what intersection is. It's what's common between both events. Events A and B are independent if the probability of A intersection B is equal to the probability of A times the probability of B. We often, and we'll see this much later in this course, with regard to often independence is assumed so that a joint probability can be determined and calculated. What's the probability of A and B? It's equal to the product of probability of A times the probability of B. So, for example, we cast a die 2 times. No, independence, your gut feel would tell you, casting a die 1 time, would the outcome of that roll be independent of, I throw that same die a second time? Would those be independent? And your gut feel on this would be, of course they are, right? They're not impacting each other. So let's say the event A is a 1 or a 2 on the first roll, and the event B is a 2, 3, or 4 on the second roll. If of the 36 outcomes, and again we could say first roll, this goes back to our product rule that we talked about before. How many different outcomes could we possibly have? On the first roll, we could have potentially 6 different outcomes. On the second roll, we could have 6 different outcomes. And so 6 times 6 is 36. N1 times N2 is equal to 36. If we looked, how many are favorable to A? 12 of the outcomes are favorable to having a 1 or 2. So if we looked at all of those 36 outcomes, we could look and say, okay, one outcome in this, one of the 36 could be a roll of 1 and a 1. So the first roll, I roll a 1. The second roll, I roll a 1. A different outcome could be I roll a 1 and then I roll a 3. Another outcome would be I roll a 1 and then a 6. Another outcome, so out of the 36, you could list them all if you felt so inclined. You can even draw a tree diagram, as we talked about, 36 different branches showing the pairings. But anyways, of the 36 outcomes, 12 are favorable to A, and 18 are favorable to B. 6 are favorable to A and B. So those would be the 6 that have a 1 and a 2, 1 and a 3, 1 and a 4, 2 and a 2, 2 and a 3, 2 and a 4, right? So those 6 different pairings are favorable to A and B. Thus, assume the equal probability of each of the 36 outcomes. We have that the probability is equal to, probability A is 12. So we roll a 1, and then whatever we roll on the second one, we're still in A. If we roll a 2, no matter what we do on the second one, that's also in event A. So 12 of those outcomes favorable to A, 12 over 36 outcomes, times probability of B, 18 over 36, and that is equal to 6 over 36, which indeed is equal to the probability of A intersection B. Hence, the events A and B are considered independent events. Okay, so that's fundamentally, that's you got to get that one in your head. Probability A intersection B is equal to the probability of A times the probability of B gives us an independence. Sorry about this slide. It's got a whole lot of words in it, as does the next one, but let's go through it. Let A denote the machine A does not break down today, and B denote that machine B does not break down today. A and B can be probability of A and probability of B can be calculated from repair records of the machine. If we assume independence, then probability A intersection B is equal to probability of A times the probability of B. Easy calculation. If we do not assume independence, then we must form a model for their dependence structure and collect data on their joint performance. Independence assumption is not reasonable if operations of machines don't affect each other. Oh, wait a minute, is reasonable, sorry, if the operations of machines don't affect each other. The independence assumption is not reasonable if machines share the same room, the same power supply, the same job foreman. This goes back to that first recording where I said, there's different ways that people work with probabilities, right? One is to assume something like, in this case, okay, I assume that the probability of machine 1 going down is independent of that events A and B are independent, that I can determine and say, okay, if I assume A going down is completely independent of B, well, suppose they do share the same power supply. So they're not going to be independent. So there's different ways you look at it and say, I assume independence, and then I work off of that for other decisions. Or I could go back and I could look and say, okay, let me do an assessment and identify whether truly I can go back through data and such and figure out, was it a reasonable assumption to say that they're independent or not? Another wordy slide, sorry. This is mostly to make the point. Suppose there are 3 events. Suppose an urn, and I would tell you that the probability examples you find in lots of textbooks have urns in them. It's a big vase, or a big bowl, basically. Suppose there are 3 events. Suppose an urn contains balls numbered 1, 2, 3, and 4. One ball is drawn at random from the urn. Let events A, B, and C be defined as the event A that you pull one ball out and the ball is either 1 or 2. Event B is that you draw a 1 or a 3. And event C is that you draw a 1 or a 4. Then the probability of A is equal to the probability of B is equal to the probability of C, all 1/2, right? Because there's 4 balls. Each of those 3 events has 2 outcomes, 2 possible outcomes mapping to them. So probability of any of those events is 1/2. Furthermore, probability of A and B is equal to 1/4, right? Because what's common between A and B is just that you pick out ball number 1. And there's 4 possible outcomes, so 1/4. Probability of B, so probability of A times the probability of B is 1/2 times 1/2, which is also 1/4. So you say, okay, that's independent. How about probability of A and C? Similarly, has a probability of 1/4, which is probability A times probability of C. And likewise, probability of B and C is equal to 1/4, which meets the qualification of, we have what's called pairwise independence. However, since what's common between A and B and C is just 1, that you pull ball 1, we have that the probability of A and B and C is equal to 1/4. That's not equal to the product of those 3 probabilities, which turns out to be 1/8. 1/2 times 1/2 times 1/2 is 1/8. Not equal to the probability as we would look at it and say, well, 1 is common. There's a 1/4 chance of getting it. So what we have is actually something we look and say, okay, what are mutually independent events? We extend what we're thinking about, right? It's not just pairwise independence. We look and say events A, B, and C are mutually independent if and only if the following two conditions hold. First, they are pairwise independence, just as we had a moment ago. And we need that the triplets, the intersection of the three, the probability of the intersection of the three is equal to the product of the three probabilities. So that is what's called mutually independent. Extending this, which will come up later as we get into statistical analysis and drawing samples and so forth. Let an experiment E consist of a sequence of n trials, T1, T2, Tn. The trials are independent if the knowledge of the outcome of any one trial does not change the probabilities of the outcomes of the other trials. Moreover, if event A sub I is associated with the ith trial, then the probability of A sub I is its probability, I 1 through n, then the probability of the intersection of A1 through AN is equal to the product. Multiple independent trials. So they're kind of related to the mutually independent events. And we'll get back to this. So this, I know I've just blasted through these things, this topic of independence. But just key thing to get stuck in your head will be probability of A intersection B is equal to the probability of A times the probability of B. Remember that one, okay? Just the two events. What is independence at that pairwise level? And that's a key thing to remember of independence, okay? It's the product of the probabilities, the two events probability. Okay, so that's one topic. The next thing we're going to look at are going to be rules of probability in this recording session. And again, back to, we asked the question of, well, how do we define a probability? And with rules of probability, what we look at and say, well, if we know other probabilities, can we derive the probability of something else based on those other probabilities? And we do this sometimes because it's really hard to calculate the one probability without knowing the others. So we use these rules as a way to kind of navigate and get us to deriving additional probabilities. So 3 different ways we're going to look at, take a peek at. Rules of probability. If A and B are 2 events in S, then they are mutually exclusive events if the probability of A and B is equal to 0. Okay, remember what mutually exclusive sets were? A and B have nothing in common. That's mutually exclusive. Now this is just saying, well, if there's nothing in common, then the probability of A and B is equal to 0. So it's saying mutually exclusive, it's kind of which one comes first, the carrot or the horse, or however that goes. Do you say mutually exclusive events, or mutually exclusive sets have a probability of 0, and the intersection of them has a probability of 0? This is saying the mutually exclusive events if probability A and B is equal to 0. If A naught is the complement of A, or not A, so you say if not A is the complement of A, then probability of not A is equal to 1 minus probability of A. So if there's only 2 things that can happen, it can rain today or it cannot rain today. If I tell you there's a probability of 0.6 that it's going to rain today, then there's a probability of 0.4 that it's not going to rain. I'm not talking about snow or anything. It's either it's going to rain or it's not going to rain. That's all I care about. Probability that the Packers will win today or not. Tell you there's a probability of 0.9 that they're going to win today. Then, if the only other outcome is they don't win, then the probability of that is 0.1. 1 minus 0.9. So you look at that. Those are complements, full complements. So those are ways of, if what you have is the information of, if you have not A, you have the probability of not A, then you can derive the probability of A. So you work with what you have. So let's go to this one. A quality control inspector has 10 assembly lines from which to choose products for testing. Each morning of the 5-day week, she randomly selects one of the lines to work on for the day. What is the probability that any of the 10 lines